To conclude this chapter, let us see how to sample random vectors which are inside a d-dimensional unit hyperball or which are lying on a d-dimensional unit hypersphere. We know that a d-dimensional unit hyperball are all the vectors in d dimensions, so all x element in Rd, for which that the norm is smaller or equal than 1. The d-dimensional unit hypersphere are all those vectors for which the norm is exactly equal to 1. We know that such a d-dimensional unit hyperball or such a d-dimensional unit hypersphere is contained in a d-dimensional hypercube, a d-dimensional hypercube for which each of the edges takes on values between -1 and 1. With this in mind, we can then define an algorithm to generate numbers which are uniformly distributed in the d-dimensional unit hyperball. First, we generate d numbers which are all IID coming from a uniform distribution on the interval 0, 1. If each ui is between 0 and 1, then 1 minus 2 ui, this is uniformly distributed over the interval -1, 1. u1 to ud thus define a location in my d-dimensional hypercube. We then set R is the sum of 1 minus 2 ui squared, so this is the norm squared. Hence it gives me the distance between my observations, my transformed observations 1 minus 2u, and the origin. If this R value is smaller or equal than 1, then we know we are within the unit hyperball, and then we output this vector. If not, if R is larger than 1, that means we fall outside the unit hyperball and we return to step 1. If we want to calculate the efficiency of this accept-reject algorithm, then we divide the volume of my d-dimensional hyperball by the volume of the d-dimensional hypercube in which it is contained, and we see that this will rapidly decrease to 0. So if my number of dimensions increases, my efficiency goes quickly to 0. If my dimension is 8, the efficiency is only 1.6%, and this is clearly an instance of the curse of dimensionality. So we will need another algorithm to sample within a d-dimensional hyperball or on a d-dimensional hypersphere. To construct this alternative algorithm, we need the following two propositions. First of all, the random variable r, so the variable which corresponds to the radius of a uniformly chosen point in the unit hyperball. This one has a cumulative distribution function of r to the power d. And secondly, if we take a d-dimensional multivariate standard normal distribution and we normalize this, so we divide by the norm, then this new vector has norm 1, and so it will be uniformly distributed on the d-dimensional unit hypersphere. Furthermore, this normalized vector will be independent from the random variable which corresponds to the radius. This second proposition allows to generate easily uniformly on the unit hypersphere. So we generate x1 to xd, so we generate d random variables which are all standard normally distributed. We generate them independently. We then combine x1 to xd in a vector x. We divide x by its norm and we return this outcome. So this outcome, this y, will be uniformly distributed on the d-dimensional hypersphere. The second algorithm will allow us to generate inside a d-dimensional hyperball. So basically what we are lacking is a radius which is different from 1. So algorithm 7 allowed us to generate on the unit hypersphere. So all of the points that we generate this way have a radius equal to 1. And now we want to fill up this sphere. We want to get to a ball, a unit hyperball. So what we are lacking is a radius, a random variable which corresponds to the radius between 0 and 1. As such, algorithm 8 is almost the same as algorithm 7, but we also randomly generate a variable which corresponds to the radius. So in step 3, we set r, the radius, is a uniformly distributed random variable, and we do this to the power 1 over d because of proposition 1 on the previous slide. So we now have a random vector x over norm of x which lies on the unit hypersphere. We have generated a radius r. Thus, in the end, we just multiply this radius with the vector x over norm of x to get a new random vector z, a random vector z which is uniformly distributed inside the d-dimensional hyperball.